Hi, everyone. I'm Pratyush. I'm a PhD student at Johns Hopkins University, and today I will be talking about our work on time-deniable signatures. One of my co-authors, Gabby, is also here, so feel free to say hi to her as well later. But let's talk about digital signatures. I'm using email as an example here. Here we see that Alice is sending an email to Bob, and email signatures. Emails come with signature authentication, and so Bob will get this email, and Bob will see that this is indeed signed by Alice's public key, and then Bob knows for sure that the message is coming from her, right? Everything's fine, and then 5 years later, Bob gets mad at Alice, and perhaps this email had some information that is problematic, even though Alice sent this email to Bob, intending the use only for Bob. Later, 5 years later, Bob takes this to the police and journalists and says that, hey, Alice said this thing 5 years ago. Let's do something bad, right? And let's think about what went wrong here, right? The point is that in an email-based communication, and honestly any other communication where you need authentication, the authentication is only meant for the receiver to verify the sender's identity, right? But the ability for them to verify a signature is everlasting. They can take that 5 years later, 10 years later, however many years later, take that to a third party and prove that this message is actually attributable to the individual sender, right? And as you saw in the example, this can have many negative consequences, including blackmail, retroactive punishment, and many such things, right? And this is a clear invasion of privacy. This is a communication between two individuals. If the second individual takes this to a third party for any purpose, this should not be the case, right? And is this a hypothetical example? Not at all. Email-based authentication has been used to attribute leaked emails and laptop-based information that journalists get to the original sender, right? And this has caused a lot of political controversies, among other things. So there has been a line of work that explores how can we deal with everlasting authenticity, right? We basically need to get rid of this property that signatures are verifiable forever. The only purpose of signatures in this case is for the receiver to verify the sender's identity, so let's limit the scope of authentication, right? And the first work in this line was on epochal signatures, and what they do there is they look at a similar scheme for group chats, and in particular deniable group chats. And what they do is they take time and they say that we're going to split time into a set number of epochs, and they have a scheme that works in that setting. Then there is the Usenix 21 work called Keyforge that assumes the existence of an always online server, and then you need the server to release key material at set periods of time for you to be able to forge old signatures, right? And the third paper in this line was the recent AsiaCrypt 22 paper called on short-lived signatures, where they assume the existence of a randomness beacon to come up with a similar scheme. And when I say a scheme, this means that basically for a set period of time, the sender decides that, okay, for the next 24 hours, a receiver can verify my identity and use the signature to attribute a message to me. But beyond, let's say, a 24-hour period, the signature actually becomes deniable, right? And so we'll dive deeper into this now. And so this is what we present in our work. We have a digital signature scheme that has time-based deniable authentication. So after a set period of time, your signatures sort of expire or become deniable. And we don't need any liveness assumptions. We don't need randomness beacons. And we can support an unbounded number of epochs in the security parameters, strictly speaking, from a cryptographic perspective, right? And as I'll show in the end, our scheme is efficient enough to be implemented with most practical application where this is an issue today. So let's look at what is a good notion of deniability, right? So let's start with a simple attempt. We shouldn't have any liveness assumptions because parties can come online or go offline at any period in time. And our deniability should not assume any behavior on that. And we will come up with a notion of sufficiently old message, and any sender can decide what this means for them. And once this time period has passed, so let's say for me the notion is 24 hours, so anyone should be able to sign as me more than 24 hours in the past, but not in the current 24-hour period, right? And so that is the notion of deniability that we want to target. So a lot of you now might be thinking, oh, like, let's try a very simple solution, which perhaps works, which is we use digital signatures and time lock puzzles. Time lock puzzles allow us to hide information behind a computational puzzle. And once you have enough number of computational cycles invested, you can get the information inside a time lock puzzle out, right? So a simple scheme we can look at in this setting is let's take the approach of splitting time into number of epochs. Let's say capital E here is the maximum number of epochs, and for each epoch we will have a signing and verification key, right? So for E epochs 1 through E, we have these many keys, and these E tuple many keys basically become your key pair, right? And to sign for a particular epoch T, you just use the signing key for that epoch, and you use the digital signature scheme signing algorithm on the message to get the signature sigma T here. And what do you put inside the time lock puzzle? You basically take all of the signing keys up to that timestamp, right? And so what will happen here is that you will set in your time lock puzzle what is the notion of sufficiently old. And whenever someone receives a signature, they can solve the time lock puzzle and get all of your old keys out from it, right? And this allows them to forge messages up until a certain period of time, but not in the recent past, where recent past is defined by the sender, right? So there is a very simple problem with a naive solution. Take the example of the Unix timestamp. The Unix timestamp is 32 bits, and so even if you split time into 2 to the power 8 sized epochs in Unix timestamps, you still have 2 to the 24 many different epochs, right? And imagine having a key pair for every single one of them. That's a very huge key size, right? And so the algorithms are not actually efficient, and we also need to worry about what is the size of like the ciphertext we generate here, right? And to solve these problems, a natural approach is to consider the fact that we have some intermediate keys. And the goal of intermediate keys here is that you want a logarithmic number of keys in the size of the epochs. And they should allow you to produce keys up until a certain period of time, right? And this should become more clear with the classic approach of using trees, right? So I'm taking the simple example that you have 8 timestamps here, and we want to sign using these 8 timestamps, and as similar to the previous approach, you have a key for each different timestamp, right? So we're going to build this tree, and what do we want the property to be in this tree is that you need this sort of delegation property, so wherever you are in a particular node of the tree, you should be able to derive the keys, which is a direct child of any node, right? And so let's say I want to generate a key that allows me to sign up until timestamp 6. I can get these 3 different keys. As long as I have the delegation property using a logarithmic number of keys, I can get any timestamp here and sign as that, right? So what's remaining now is to get a succinct representation of node keys, and also you need a way to extract child keys from the parents, right? And this is an age-old approach used in cryptography using identity-based encryption, but because of delegation, we need this hierarchical property. So an example here is that you have a space of identities where there's a hierarchy defined, and the highest individual or party, so I'm taking the example of a university here, so the university has .edu access, and then they give it to jhu.edu, and then they can delegate to cs.jhu.edu. These are basically the identities of the keys, and you can get individual email addresses or keys at the bottom here using this delegation, right? So yeah, I'm going to quickly hint at how we construct this. This is the signing key pair, and what we're going to do here is that for any timestamp, we will have the binary string representing the timestamp, and it will be one of the leaves in this tree. And then the message actually lives beneath this, right? So let's say you want to sign at this timestamp, you get the key until there, and you delegate one more time to get the message, particular message and timestamp key, right? Okay, all is fine and well, but I'm using a Hive scheme. I'm talking about signatures, so how does this work? There is a very simple way to convert a Hive key to be used as a signature. You just generate a key on a particular message, or using the message as the Hive identity. And then for verification, you just encrypt a random message string, and then you test the description using the key that you generated. If the decryption succeeds, you know that the signature is indeed valid, right? And so the ciphertext of the Hive scheme actually becomes like a signature. Okay, there are still some tricky issues remaining, because I am saying that you can forge signatures in this way by doing delegation, but then delegation should be indistinguishable. So what you need is a key indistinguishable Hive scheme, because what you require is that you take a signature, someone forges it, it should be indistinguishable from the original signature, otherwise it can still be attributed to the original signer, right? And for this purpose, we use Hive schemes which do have this property. One of them is Luca Waters, the other one is CLLWW using the BN254 curve. And these are some of our numbers we get. Yeah, using the CLLWW scheme, we actually do get a pretty efficient implementation. Yeah, we hope people use this for better privacy. Thank you.
All right.
Thank you, very nice. So if I understand correctly, you have this very cool mechanism of getting like all these signature keys in like a succinct way, but you're still using time lock puzzles then? Yeah. Why do you need time lock puzzles? Can I just publish my secret key?
Yes, you can do that. You can publish your keys, but that requires the liveness assumption that you will come online at some point after signing. The way the time lock puzzle allows us to do this sort of control leakage is that with the signature, you allow the 3 keys in the tree, which are logarithmic in size, and that you put that inside the time lock puzzle. Someone can solve it, and then they can forge signatures in the past using your identity. And that sort of gives you plausible deniability without coming online later.
Okay, thanks.
Thanks for the great talk. So when you are sending email to fight spam, your email provider signs your email, and this is not deniable for a judge. And can your scheme be adapted to be run by like Google or other big parties there? Are they willing, and what will be the practical issues there?
The practical issues perhaps would be that compared to like a usual signature scheme, I guess we're still like maybe a magnitude of speed slower. So they'll have to deal with that. And I guess like you still have to deal with this like dual problem of like the individual sending the email, and in the spam setting, you're saying like the email server signs it as well. So that will give you an extra layer of difficulty to deal with. Yeah.
Go ahead.
So thanks for the presentation. Very interesting. You said about people using this. Is there an implementation of any sort that people could try out and deploy in practice?
Yes, we do have an implementation. I think the code is public already, but if it's not, we'll put a link to it somewhere. But yeah, we have an implementation. It works. And yeah, we hope people use it.
Yeah. Try it out.
Yeah.
Two things. Like, first of all, did you think about other application about your scheme, like except like this email scenario?
Yeah. So I think like in any form of communication where you're using authentication, so whether that be instant messaging or group chats, anything like that, you can still use this type of communication. Perhaps there are government services where it makes sense to use a similar type of authentication, but I mean, as far as I know, and people in this room know, getting the government to do anything as hard as we know it is. So Yeah, hopefully in those instant message type settings, you need schemes which are blazing fast, which you need like signing times in a few milliseconds, not like 100 milliseconds. So that's still like the barrier that exists to ship this in like an instant messaging type setting.
Just quick, another question if I have.
It's you're keeping us from our coffee. Maybe you can ask offline.
Yeah.
All right, let's thank our speaker again.